Also, we have established some formula for the loss matrix, and also from the loss matrix concept, we found the confusion matrix. So in the confusion matrix here, that we have seen that if a point is actually coming from a particular class, but it is classified in some other class, then it generates an error. Now, if the error is occurred, then how to handle this error? So there is a two things that we have seen. One is called that uh, if the errors will have the different weights. So if the errors have the equal weights, then this only the probability comes into the picture. Okay, and if the errors have the if the errors have the equal weights, and if the errors have the different weights, then you have to consider this cost. Okay, there's a misclassification cost. So now if you have the misclassification cost, then you need to generate the loss matrix. So we have demonstrated with uh, two class classifications problem, and this problem can be understood in a more generalized way for the M class classifications problem. So that you can see, and we have taken an example for this example for the disease like this. One tumor is called I mean, if the doctor is going to diagnose a patient with malignant, the tumor is a malignant or it is a benign or non-malignant tumor. So that we have seen a couple of things and how you can minimize this average risk. Okay, so it is already there in Dudart book, so more derivation is there. So you need to, I'm just I mean explaining to you with some important parts, and these most of the things I may not be able to tell you because here there is no provision for doing means drawing these things. Okay, so if it is broad, then I would have I mean written all and each and every term appropriately. So anyway, so now today we'll see that multivariate Gaussian things that we'll see. There's a two if you have, so all these things that we have done. Yes, discriminant. Today we'll establish these discriminant functions, or we have seen the concept of the discriminant function. From the discriminant function, we'll establish today a linear discriminant boundary, decision boundary, or you can say the linear discriminant functions, or that we'll see today. And uh, these things, yes. So today we'll see the base classifier for the normal distribution. So normal distribution for multivariate Gaussian. So this formula is common to all of you. Suppose Pix. Okay, so I means ith class. Okay, so if you have this C number of classes, then for each class one density functions will be attached. So the formula is 1 by root over 2 pi to the power n. Determinant of sigma I is means this is this determinant for the ith class. So that's why the subscript is written here. This sigma I. So determinant of sigma I to the power half exponential of minus half xi. X is a uh, n-dimensional vector. Okay, so it is like this n cross 1, it is a column vector, and this is a mu I. So mu I is a mean vector. So for this, for each ith class you will have one mean vector. Okay, so now each dimension also n cross 1, then transpose, then this is a variance covariance matrix sigma I inverse. It means for each class there will be a variance covariance matrix. So that is why it is sigma I inverse, then xi minus mu I. Okay, and you have the prior probabilities, that is capital P1, capital P2 till capital PC. Okay, so now today we'll see two different cases. Now this, if you just use, you want to if you, so it is a one example. So this is a one example that how the base classifier can be used for a normal distributions. So now firstly we'll see one example number case 1. Now in the case 1, let these are few assumptions that you are going to make. So first one is that let P1 is equal to capital P1 is equal to capital P2 is equal to capital P3, capital PC is equal to 1 by C. I mean the prior probabilities are equal, all the prior probabilities are equal, and it is 1 by C. And your distribution is a normal distribution. First assumption is that the distribution is a normal distribution. Second assumption that you are going to make that these prior probabilities are equal. Third assumption is that the variance covariance matrix are equal, and not only equal, it is also an identity matrix. So sigma 1 for the first class, sigma 2 for the second class, till sigma c for this cth class. Okay, so for each class the variance covariance matrix is equal. Not only equal, it is an identity matrix. So you are going to have quite a few of assumptions, and under the assumption then you are going to draw a conclusion. So now we'll see that how a conclusions can be drawn. Now after making these many assumptions, now you could put x is a test vector, so it is in vector, so put x in ith class. You can put in ith class if capital Pi small pi x is greater than is equal to capital Pj small pj x for all j is not is equal to I. Okay, so this is the base decisions rule that we have already seen. Now we'll use that. Now the formula that I'm going to have, I have written. So now if I just use it, capital Pi small pi x is greater than is equal to capital Pj small pj. Okay, now I am going to write the formula 1 by root over 2 pi to the power n determinant of sigma I to the power half x power minus half x minus mu I to the power transpose sigma inverse x minus mu I. So now I am putting these things for each density functions. Now how will be the scenario? So now as you can see that this variance covariance matrix is an identity matrix. Okay, this sigma is an identity matrix. Now if you put now determinant of sigma, it means the determinant of identity matrix is 1. Then square root of hello, am I audible?
Yes.
Yes, sir.
Yes.
Yes,
Now this variance covariance matrix is an identity matrix. Okay, now the determinant of identity matrix is 1. Square root of 1 is also 1. So now I am not writing it. Okay, then I am simply writing capital Pi. Okay, 1 by root over 2 pi to the power n. So I am not writing this is a 1 by determinant of sigma to the power half, as it is 1. Are you understanding me? Are you understanding me? Why I am not writing this one? Means why I am not writing this 1 by sigma I to the power half. Okay. Next is exp of minus half xi minus mu I transpose xi minus mu I. Okay, so I'm not writing sigma I to the power inverse because the determinant this sigma is an identity matrix. Then this sigma inverse is also an identity matrix. So now if you multiply anything with the identity matrix, so the results will not be changed. So that's why I'm not writing here this sigma in the inverse I. As this sigma is an identity matrix, now sigma inverse is also an identity matrix. Okay, now if you multiply anything with the identity matrix, so the results will not get changed. So that is why we are not writing this sigma inverse I. So we are simply writing that is a minus half xi minus mu I transpose, or here I have written t. You could have written also this one. I mean simply dash. So if you simply write the dash also, it is also prime. So minus half xi minus I greater than is equal to pj 1 by root over 2 pi to the power n exp of minus half xi minus mu I t, then xi minus mu j t and xi minus mu j. Okay, if and only if. So this symbol is called if and only if this condition will be satisfied. So now this as you can see that prior probabilities are same. So now this pi pj will be cancelled out from both the sides. So our first assumption was that this p1 is equal to p2 is equal to p3 is equal to 1 by c. It means that you can cancel out capital pi from both the sides. So pi pj will be cancelled out. Okay, so now what you are going to have next, what you are going to have, you have exp of minus half. Okay, exp of minus half xi minus mu y transpose xi minus mu y greater than is equal to exp of minus I xi minus mu j transpose xi minus mu j. So now it is an exponential. Now if you have to take a logarithm functions, okay, you will have to take a logarithm. Okay, now if you take the logarithm, then these things, the exponential term will be removed. Okay, I mean x will be removed. So now if you take, so we are going to take the logarithm. So now log of exp of this thing. So now if you take the log, then what you are going to get? You are going to get minus half because logarithm is an increasing functions. Okay, so now logarithm is a, you can say, the monotonical increasing function, and if you use the log, so these things will be, this is a, the exponential will be removed. So that's why we are taking this logarithm function, and it is also monotonical increasing function. So that we are taking this log if and only if minus half xi minus mu y transpose xi minus mu y greater than is equal to minus half xi minus mu j transpose xi minus mu j for all j is not is equal to I. Okay, now what I am going to do, I am just bringing back the right hand side term in the left hand side, and I am just shifting the left hand side term in the right hand side. If you do this thing now, if you have minus half, now this minus half into half will be cancelled out in the both the side. 1 by half you have in the left hand side, and 1 by half you have in the right hand side. Now 1 by half will be cancelled out. Okay, now I am just bringing back this xi minus mu j transpose xi minus mu j in the left hand side. Now if you do it, what you are going to get, this xi minus mu j transpose xi minus mu j greater than is equal to xi minus mu j x minus mu I transpose xi x minus mu I for all j is not is equal to I. Okay, so now this is a very interesting classifier that you could derive from a base decisions rule. Okay, what is it? Now you could put x in ith class. You could put that x in ith class if xi minus mu I transpose into xi minus mu I is less than is equal to xi minus mu j transpose xi minus mu j. Okay, then you can put x in ith class according to base decisions rule. So now what we are exactly doing? So we are calculating the distance. It is just nothing but it is simply a distance. We are calculating the distance between x and mu I, where mu I is the mean. Okay, so you put x in ith class if the distance between x and mean of the ith class is less than and equal to the distance between x and mean of all the other classes. Then you put x in the ith class, because as you have already got an assignment on this distance based classification techniques. Okay, if means quite a few, I mean some of you has having some doubt. So this is the things that we are doing. So I'm just repeating that we are calculating the distance between x and mu I. So that's why xi minus mu I. So it is the format. Okay, so it is simply just a that the distance can be written in the way x1 minus mu1, x2 minus mu2. One form will be written in row vector, another form will be in the column vector. Okay, then x1 minus mu1 into x2 minus mu2. That's it. So this transpose is there, so that is why one will be this. If it is a column vector, then if you do this transpose, you will have the row vector. Okay, and one row vector and another the column vector. If you just multiply it, you will have this distance formula. So we have already established this formula from the previous class. So now that is the concept. So we are, so if you can put x in the ith class. Okay, if these things is less than is equal to these things, and it means that you are calculating the distance between x and mu I. So mean, you are just calculating how much deviation is there from the mean, so that you are calculating the distance between x and mu I, where mu I is the mean, and you put x in the ith class if the distance between x and mean of the ith class is less than or equal to the distance between x and mean of the all other classes. Okay, then you can put x in the ith class. Okay.
Sir, excuse me, sir.
Yes.
Sir, x minus mu I transpose multiplication by x minus ui. These are matrices, right?
It is not a matrix, it is a vector.
Vectors.
Yeah,
Vector.
yes, sir. So when we multiply, so let's say for a multi-dimensional vector, so how will we comparing these two vectors, row by row?
No. So one vector is a column vector, another vector will be a row vector. Now you have to just multiply one by one. Now, matrix, I mean, this is a vector. That means how do you do it? If you have x1, x2, x3 in the row, and in
Row
the
from
column, if you
first.
have x1, x2, x3. So now x1 square, x1 into x1, then x1 into x2, x1 into s3. These are the way.
Yes, sir. Now we have to let's say we have to compare that whether it is greater than or equal to. So how will be comparing that? I'm asking.
For each point, you will have to test. Okay, so you have to compute this the distance between the for I mean the data point that you are going to check, isn't it? Suppose in the test, for each test data point you have to check with the mean of this class. So you have to apply the equivalent distance. So actually these are the minimum distance classifier. So this distance will be a equivalent distance. It may be a city block distance. It may be a chessboard distance, so on. So it is a generalizations way of derivation for the distance based classifier. And this minimum distance classifier is coming from the base decisions rule with the certain conditions, with the certain assumption that we have made. So we have made quite a bit of few assumptions. So if you don't meet all the assumptions, then you cannot derive it. The distribution must be a normal distributions. The variance covariance matrix must be identity matrix. All the prior probability should be equal. So under the assumptions, you could derive a minimum distance classifier. I'm just telling you how this minimum distance, what is the mathematical background? Because as you have got one assignment on the minimum distance classification, I mean this distance based classifier. Now what is the mathematical background of the minimum distance classifier? I mean from where it is coming. So you'll be interested to know from where it is coming. And it is coming from the base decisions rule. It is coming from the base decisions rule. Okay, you take x and you have these many means. How many you take x, means test point, and you have these many means. You calculate the distance of x with all these means, for all the means, and you find that whenever it is minimum, then you put x in that class. That is the concept. You take x and you have these many means, and you calculate the distance of x with all these means, and find that whenever it is minimum, you put x in that class. That is the concept. That's why it is called the minimum distance classifier. And it is coming from this base decisions rules. I mean this concept, this is a multivariate Gaussians, and from the base decisions rule under this certain assumptions. Hello?
Yes, sir.
Hello, am I audible to all of you?
Yes, sir.
Yes, sir.
Is that clear?
Yes, sir.
Good.
Hello, sir.
Yes.
Sir, in the example you have given in the last lab assignment, there X was having 4 attributes like those sepal length and petal length. Sir, how are we going to match those? Are we just going to subtract each component X of sepal length minus mean of sepal length, and we are just going to sum up all those to get the distance, right?
What you could do, if you have the 4-dimensional feature vector, you take all the feature vector in one column. Okay, you take all the feature vector in one column because you'll have only one mean. Mean is a point. Mean will be a single point. So please note it. Mean will be a single point. Okay? If you just take only one feature, staple length, from the staple length, you will have only one mean. Okay? If you have this staple width, if you have only one mean, mean will be a single point for each feature. Okay?
So
and
that
what you have to do?
sir, yes, sir.
Yes, I'm explaining to you. So if you have this 4-dimensional feature vector, okay, for each feature vector, okay, you have this for one feature vector, you will have one mean. For the four feature vector, you will have the 4 mean. If your feature vector dimension is 50 cross 4, then after computing these things, you have 4 cross 1 or 1 cross 4. Sorry. If you have the feature vector dimension 50 cross 4, then after computing the mean, you will have to do the column-wise mean, not row-wise mean. If you do the row-wise mean, so it will be wrong things. You have to do the column-wise mean. If you do the column-wise mean, each column you have one mean. Okay, for this one feature you will have one mean. Next feature you will have another mean, and you have the another feature, you will have another mean. So 50 cross 4 will be boils down to 1 cross 4. You have the 4 mean. Now for the each mean, so that's why I'm telling now you have X and you have these many means, and calculate distance of X with all these means and find whenever it is minimum, put X in that class. Are you getting?
Sir, X is also having those 4 features, na sir. So then how are we going to find the distance from a vector to a mean, which is a single point?
No. For you have the one mean, na. So whenever you are going to test it, na, in the test it, you take one column, means one feature vector, or if you could arrange all the feature vector in only one column. Okay, first column, suppose you have 50 points. Second column, you have 50 points. Now in the second column, this 50 points, you can append it after this 50 rows. Then third column, you can append it in one column. I'm just telling that all the columns you can append it in only single column. Then you take the one, you take the distance now. You have 50 whenever you have the test data sets. So now means what is the size of the test data set?
The total 150 cross 4.
Total 150 cross 4, but means you have the 60% of the, I told you na, 60% will be the training data set, and this training data set, in the 60%, the mean can be computed from the training data set.
Yes, sir.
Okay, the mean can be computed from the training data sets. And then whenever you're going to do the test data set, I mean the rest 40% that you'll have to test it, you'll have to just check that means what is the close proximity. Actually, you're trying to find the close proximity. Then you can see this distance.
So when we are finding mean, we will be having four means, right? So mean
Huh.
for the sepal length and mean for the petal length and those for
Hmm.
the two widths also. Sir, X is also having the four attributes, no sir? Sir, X is also having petal length and sepal length and petal width and sepal width. So how
Exactly.
are we? Yes, sir. So then how are we going to find the distance from X to the mean? That is what I was asking. You also said to consider all those four features to find the distance. I was confused in finding the distance between x vector and those means.
Xi, you have this. So what is the formula of the equivalent distance? Square root of half of xi minus, okay, yi. So your mean is there. Okay. You take one point and you take the difference between this mean. First mean, okay, from all the points means all the 50s means total you have suppose how many points that you are going to have.
So 20 points, sir.
Hello.
Yes, sir. 20 points, sir, for test class for each.
Hello. So am I audible?
Yes, sir.
Yes, sir.
I'm just telling you make only one test file. ठीक है? You make one test file and this dimension of the test file will be n cross 1. I mean you can append all these I mean all the column this column vector, I mean this all the features into only a single column. All the features into a single column.
Sir, this part
Then
you're talking.
from the row wise you can do it. All the columns. Hello.
Yes, sir. You are audible, sir. Kindly continue, sir.
Um, Excuse me, sir. Hello.
Hello. I think so. There is some network problem probably. Are you understanding me? You just make a only single file where all this you means this is a test vector dimension will be this n cross 1. I mean you append all the feature in one column.
Sir, this is, sir.
Hello.
Yes, sir.
Yes, sir.
Hello.
Yes, sir. You are audible, sir.
Yes, sir, you are audible, sir.
Sir, but I have done like this, sir. Sir, mean have 4 components.
Can you hear my voice?
Yes, sir.
Yes, sir.
Huh?
Yes, sir.
Yes, sir, you are audible,
Hello?
Yes, sir.
Sir, but this can be done like this also. Each centroid has 4 components. Similarly, the test points, each test points have 4 components. So we can directly compute the distance also. Na? Sir, each centroid
What you are saying?
has 4 means. Na? So 4 component, each
Hello?
centroid has 4 component. And similarly, the test points also have a 4 components. And we can directly compute the distance. Na? And there is no need to keep in column.
I'm sorry. So there's a problem in network. So can you all hear my voice?
Sir, we can hear your voice clearly, but can you hear our voice?
Yes, it's not clear. So I'm just, shifted my network from college net to mobile. Okay. I think it will be okay. Okay. So now what I was trying to say. So you have to make a one single file where all the feature vectors will be appended in only single column. Okay. You know that from 1 to 50. These observations for this first feature 51 to raised 1, 51 to 100, it is for the second one. Okay, 100 to 49, you could means 100 to 50, 100 to 150 for the third feature. Okay, and these things, then you can have it is in totally your xi is equal to 1 to n, then you take the distances. Am I clear?
Sir, that means in sequentially we'll be writing the 4 features for each class.
Yes, this is the 4 features for each class.
So,
that
Sir,
is a
in the
trick. हाँ बोलो.
So each
Sir,
feature.
in the file you give.
हाँ.
So each feature has 50 instances. So 15 to 4 for each class.
15 to 4 for each class.
Okay, sir.
ठीक है.
Sir,
But sir, in the when we are calculating centroid, I'm just asking, can we just do it using 2 features instead of 4?
You can do it. No problem. No issue. You can also take one feature. You can also take one feature. You could take one feature, you could take 2 feature, you could take 3 feature, you could take these 4 features. Okay, but then you see this. What is this? Accuracy of your whenever you're going to test it, then you need to find this. What means what is the accuracy? Means whether so is it the case if you just decrease the feature, your classification accuracy increased, or is it the case that if you increase the feature, your classification accuracy is decreased? That you need to check. Okay, just wanted to give it to this example to see that this is a simple things, very trivial way of doing these things. So just calculate the distance from the mean. Okay, and calculate the distance between x and mu y. Okay, where mu y is the mean.
Excuse me, sir.
For each class, you will have only one mean. So can I go further? If you don't have any doubts now.
Excuse me, sir. Can you hear me? Sir, actually, I wanted to ask, like mu I is 1 cross 4 vector. Here, if we consider 4 features, so x is a particular point which has 4 coordinates. So for a particular point, it would also be 1 cross 4 vector, right? So 1 cross 4 vector minus 1 cross 4 vector, it would be like this, and then we will do it for all the test points. Yes, sir. Okay, so thank you.
Okay, you first do it, na? You just try it. So because whenever you are going to implement it, so then you will be facing this actual thing. Then this mathematics portion that you need to, it will come. Just Sir was explaining to me in this way. So the formula is xi minus mu y transpose xi minus v. It is simply just one is a, if you take this, if you x is having the 2 component x1 and x2, then you can simply do it. Okay.
Okay, sir. Yes,
x1 minus
mu1
and x2 minus mu2.
X is just a particular point which has 4 coordinates, so we would represent it as 1 cross 4 vector, And likewise, mu I is a centroid, like means so it's centroid.
Exactly, it is a centroid.
Yes, sir. Okay, sir.
Excuse me, sir.
Hello?
Yes, yes.
Sir, X is also a 1 cross 4 vector. Mu is also a 1 cross 4 vector. Sir, we can find the distance as it is, no, sir. Sir, what is the need of converting all those 4 feature vectors into a single column?
No. It is for this, you are not understanding. It is for the one features. No, if you have the multiple feature, then you take the second column. Then you do the same way that you have done for the first one. Then you take this third one. If you have the more number of features, then your discriminating power will be maximum. If you have these more features, then you have the discriminating power will be more important, because it may so happen if you take only single feature, then this same feature, the value of these features will be same for this one class, and the value of these features for the another class are same. Then how we are going to distinguish it? Suppose if I am going to distinguish with you and with your friend, and I am taking only one feature, so that is your ear. Now the shape of your ear is same as this. I mean, taking this shape of your ear as a feature. Now shape of your ear is same as your shape of ear of your friend. Now how I am going to distinguish it, you and your friend? Are you understanding me? What is the necessity of taking these multiple features? Because there's a proximity measure. You have to take the proximity measure. So you think in a different classification way of things. Okay, don't be stuck in a particular point where I'll be doing only one features. I mean multiple features. I'm just taking you the example. It may so happen this one feature is not enough to distinguish between two classes. Okay, so that is why more number of features is important. One features may not will give it to this correct classification accuracy. You can check it with this. If you take all this separate step length, then you can check. And if you take these multiple features, then it may so happen na the same features. If you take the same features, the feature value for both the classes are same. Then if the values are same, so there is no difference. Distance is 0. If the values are different, okay, then you will have the distances. If the values are same, so there is no differences. Distance is 0. Then how are you going to distinguish it? Okay.
Yes, sir, I got it. Thank you.
Clear now? Or you have doubts? Okay, so we'll see in the lab class. Okay, so let me just complete. Okay, so let me just complete. Okay, so this is a one case. I have explained to you that it is coming from this minimum distance classifier. It's coming from the Bayes decision rule. This is case 1. Now case number 2. Now in the case 2, that m is equal to 2. That is m is equal to 2 means that is class is 2. So I am just explaining with the for 2 class classifications problem. It is always better to explain with 2 class classification problem. So that's why I'm taking m is equal to c, or you can take c is equal to 2. Okay, and I am going to make a one assumption. So our previous assumption was variance covariance matrix was equal, and also it was an identity matrix. Now here the variance covariance matrix are only equal, not identity matrix. Okay, the sigma 1 is equal to sigma 2 is equal to sigma. That's it. Now if you apply the Bayes decisions rule, that what you are going to get, capital Pi small pi x, you put x in the ith class. So your interpretation will be like that. You put x in the ith class if you put in x in the first class, because as I am considering these 2 class, then you put x in the first class if capital P1 small p1 x greater than is equal to capital P2 small p2 x. Okay, if and only if. Now capital P1 is a prior probabilities. Okay, and then 1 by this P1 is given to you, P2 is given to you. It is constant. Okay, the 1 by root over 2 pi to the power n, determinant of sigma to the power half, exp of minus half x minus mu1 vector it is xi minus mu1 transpose sigma inverse xi minus mu1 greater than is equal to capital P2 1 by this root over 2 pi to the power n sigma to the power half x3 of minus half x minus. So here this should be below x. Okay, it should be on dash because it is in vector. So I missed to write this dash. X minus mu2 transpose the sigma inverse x minus mu2. Okay, now 1 by root over 2 pi to the power n and sigma to the power half, because this sigma 1 and sigma 2 is sigma, so that's why it will be cancelled out in both the sides. Okay, now you take logarithm, so apply logarithm, so it is a natural log, means its base is e, not base 2. Okay, so we are applying the natural logarithm, so now your base is e. Now we are going to have log p1 minus, now if you take these things, log p1, okay, of exp of these things, and these things will be come up. Okay, log p1 minus half x minus p1 transpose sigma inverse x minus mu1 greater than is equal to log p2 minus half x minus mu2 transpose sigma inverse x minus mu2. Okay, now what I'm going to do, so I'm taking log p2 from right hand side to left hand side. Okay, now if you do it things, so before doing it things, so we are doing some calculation. You just see log p1 minus half, then these things, the multiplication that we are going to just do it in this way, half into it is just x transpose sigma inverse x minus, I'm just multiplied. Okay, x transpose sigma inverse x minus x transpose sigma inverse mu1 minus mu1 transpose sigma inverse x plus mu1 transpose sigma inverse mu1. Okay, although it looks little bit of clumsy, okay, but it is very simple. Now next is greater than is equal to log p2. You can do it by yourself also, minus half x transpose sigma inverse x minus x transpose sigma inverse mu2 minus mu2 sigma inverse x plus mu2 transpose sigma inverse mu2. Okay, now you see x transpose sigma inverse x, and here also x transpose sigma inverse x, that will be cancelled out. Okay, in the left hand side, within the third bracket, you are seeing x transpose sigma inverse x also there, and here also x inverse x transpose sigma inverse x, it will be cancelled out. Okay, now the second term, you just look at x transpose sigma inverse mu1. Now what is the dimension of x transpose? Now x is a your n cross 1. Now it is a transpose, it will be 1 cross n. Now 1 cross n, now sigma is a symmetric, or it is a square matrix, 1 cross n into n cross n, and mu1, it is a n cross 1. Now it is then if you just do it, you will have the scalar 1 cross n into n cross 1, it is a 1 cross n. Now 1 cross n into n cross 1, it is 1 cross 1, it is in scalar. Clear? It is the scalar, and this term, it is just a mu1 transpose sigma inverse x. Okay, so now it is just a transpose of x inverse sigma inverse mu1. So that's why both the terms are equal. Just look at x inverse sigma inverse mu1 and mu1 inverse sigma inverse x. Now it is just transpose of this one. So now if it is a transpose and it is also a scalar, then both the terms are equal. So that's why we are taking the minus 2 x transpose sigma inverse mu1 plus mu1 transpose sigma inverse mu1, which is greater than is equal to log p2 minus half that x transpose sigma inverse mu2 minus mu2 transpose sigma inverse x. Now if you just do the transpose, now this thing is scalar and this thing is scalar. Now both the terms are equal. Why it is equal? Because if you could do the transpose of this quantity, you will get the same things which is written over here. Now that's why we are writing minus 2x transpose sigma inverse mu2 plus mu2 transpose sigma inverse mu2. Is that clear to all of you? Why we are writing it? Because in these things, that is a linear algebra, that if it is a scalar and if it is things, it is also a scalar and it is a transpose of the things, it means both will have the same quantity. So that's why you could write in this way. So now what I'm going to do here in the next step, obviously it is an if and only if. Now log P2, so I'm bringing back log P2 in the left hand side. Now if I'm going to do it, then I will have log P1 minus log P1 minus log P2. You will have the log P1 by P2. Okay, greater than is equal to. Now this is an you have this half this here. Yes, obviously here this half will be cancelled out. Okay. Sorry, so it will not be cancelled out. So you will have this log P1 P2. Now this minus half will be go to the this side. Okay, in the right hand side. So the minus half of minus 2x transpose sigma inverse mu1, these things will go to the in the right hand side. If you do it, so now the minus half will be the plus half. Now this log P1 by P2 greater than is equal to, you take half as a common term, then you have 2x transpose sigma inverse. Okay, this is a mu2 minus mu1. Okay, that you could get, plus this is a constant mu1 transpose sigma inverse mu1 minus mu2 transpose sigma inverse mu2. This is the same things that you can get. And this, if you just insert, or this if you just insert half within the bracket, what you are going to get, log P1 by P2 greater than is equal to the half. You are just inserting half in within this bracket. Then you have x transpose, the half into 2 will be cancelled out. X transpose sigma inverse mu2 minus mu1 plus mu1 transpose sigma inverse mu1 minus mu2 transpose sigma inverse mu2 divided by 2. Okay, now just see. Okay, now just see that if you just look at in the previous one, that is your sigma 1 sigma 2 is equal to sigma. Now you will have only one term. What is the term? X transpose sigma inverse x. It is quadratic in x. It is quadratic. I hope that you know the meaning of the term of the quadratic. So it is quadratic in x. X transpose sigma inverse x. It is quadratic in x. Okay, so now if it is quadratic in x, it means that suppose you will have some x1, x2, x3, then in the row, I mean if you have a row vector x transpose, in the column you have x1, x2, x3. Now if you sometimes you will have x1 square, then this x2 square, then you have x1, x2, then you will have some square term. After a certain time you will have some square term. So that's why you are going to have this quadratic. Okay, now here as we have one assumptions, this sigma 1 is equal to sigma 2 is equal to sigma. Now this quadratic term has been vanished. This quadratic term has been vanished. If it is vanished, then the log P1 and P2, it is a constant term. Okay, sigma inverse mu1 transpose sigma inverse mu1, you can compute it. So it is a constant. Okay, this is minus mu2 transpose sigma inverse mu2, that is by 2. It is also the constant term. You can easily compute mu1 minus mu2. Okay, and you can also compute this sigma inverse. So it is all of the constant term. Only you are having this x, which is a linear, which is this linear in nature. So that's why the decision boundary will be, this is a linear discriminant functions, or you can say this is called the discriminant functions between classes is linear. Why it is linear? Because due to this assumption sigma 1 is equal to sigma 2 is equal to sigma, this quadratic term has been vanished. Okay, and that's why this is a linear and this is a discriminant function. I mean the decision boundary is a discriminant function. And if it is, if sigma 1 and sigma 2 is not sigma, okay, then you could have taken here, I could not this 2x and sigma 1, you could have write here x transpose sigma 1 minus sigma 1 minus sigma 1 inverse x, then you have this sigma 2, you have the both the terms sigma 1 inverse and the sigma 2 inverse, then this decision boundary will be this non-linear in nature. So that was, it was a non-linear decisions boundary. Okay, now here as you are having the only constant term, this is an all other terms are the constant term and this only the x is there. So that this is an x, suppose y is equal to ax kind of things. So it is a linear decisions boundary. But if the sigma 1 and sigma 2 is not is equal to sigma, then your decision boundary is a non-linear. Then your decisions boundary is non-linear in nature. So now if the case that if there's another case, suppose the distribution is normal distributions, okay, and instead of taking these two class, if you are going to have the three class and for each class you have the three normal distributions and your sigma 1 is equal to sigma 2 is equal to sigma 3, it is also a sigma equal, then what will be the decision boundary? If you have three normal and sigma 1 and sigma 2 and sigma 3 both are equal and which is only sigma, then what will be the decisions boundary? Can anyone tell me?
It's a linear.
Linear.
Huh? It should be
Linear.
You are going to solve a multi-class classification. If you have the two class, it's fine. If you have the three class, then it should be a piecewise linear decision boundary. Because you take this class 1 and class 2. You take this class 1 and class 2. Okay, then class 2, class 3. Then class 1, class 3. Okay, you have these three lines. You have the three lines which are discriminating between these two classes. So it's why I say piecewise linear function, or you can say piecewise linear discriminant functions, provided that the density function is normal. Provided that density function is normal. Actually, the linear model is that x is a vector, x transpose A is a constant. You can write or you can expand it x1 a1 plus x2 a2 plus x3 a3 plus ... xm am, which you could get from these equations. All the terms are the constant term. Only x is there. So that's why it is a linear. Now you could, from the discriminant function, you have understood this is a linear discriminant function. Linear discriminant functions you could have from the base decisions rule. You could derive a linear discriminant functions under the certain assumptions. What are the assumptions? Your density function is normal and your sigma 1 and sigma 2 is equal to sigma. And if you just extend it for the multi-class also, you will have the piecewise linear functions. And if your variance covariance matrix are not equal, then you will have this non-linear boundary due to this quadratic term. You will have this quadratic term. Okay, you will have this quadratic term because you will have this square term. You will have so that's why you will have this thing. So these are the very important, very important things. If you follow any book, either from this Dudahat book or the Fukunaga book or this other book also, you will have this derivation. And also these things is already there. Whatever I have explained to you, it is already written. Okay. And another thing is that this type of examples will be given to you. So it is just a mathematics. Okay. So before understanding these things now, so this derivation is you'll have to do more practice, because in exams you will have to draw it. I mean, sorry, you'll have to derive all these things. So these are the things that you need to focus. And also this based on the covariance matrix, that the shape of the density functions will vary. It will be a ellipsoidal figure. I mean, the shape of the density function will be ellipsoidal. Shape of the density function will be parabola, or it will be a hyperparabola, or you will have the pair of lines. I mean, the discriminant function that you are going to derive. So based on the certain condition, you will have the ellipsoidal shape, you have a parabola shape, you have a hyperbola, and you have a pair of lines. So we have already seen the concept of the pair of lines, which is a piecewise linear discriminant function. So in the next class, we'll see these different. I'll also today surely I'll just share this PPT so that you just go through it. I'm after this class, I'll just now send it so that you will have. I forget to send. These are the things that this is this term x transpose xi. This is a quadratic term that I already explained to you. It is a quadratic term, and if it is same this quadratic term, that you could have that these expressions from the expression that you could derive it. So you just see that this function is equal. It is a linear when it is a quadratic I mean the discriminant function is linear when this sigma is equal to sigma. Okay. And if it is now if you just add a sigma square into y, then this you just expand it, so it is not very tough. I mean there's a two certain conditions. One is a normal condition, another is this non-normal distributions. If it is a normal distributions, then you will have this situation. If it is a non-normal distributions, you will have the another situations. So we'll see all these things. Means what is this graph? Okay. If it is a normal, then the decision of the hyperplane will be something like that. If it is a not normal, so the decision boundary is like that. So under the condition is sigma square into I. And we'll see that if the features, so there's a concept that features are statistically independent. So when you would say these features are statistically independent, what is the meaning of statistically independent? Anyone knows the meaning of what is the meaning of statistically independent?
Covariance will be 0.
Very good. Covariance will be 0.
0.
Huh? Good, very good. Achha, so I just wanted to take some extra class because so when you guys are free apart from Monday, Tuesday, and Friday, when is a free slot? So can you just intimate me?
Sir, for IS, we are having free slots from morning to your lab.
No, afternoon you're free. 4 to 5 any day. I mean, except Wednesday.
Sir, Saturday.
Saturday. Okay.
Saturday. Friday.
Friday you have already class from 9 to 10, 10 to 11. Thursday are you free?
Sir, after 4:10.
After 4:15, na?
Yes, sir.
Okay, so I'll take.
Thursday we have class.
Sir, we have class, sir.
Thursday you have class? Every
Yes, sir.
Thursday?
Yes, sir. Software engineering have class.
Okay, okay. So probably Saturday we'll see. Okay. So this Saturday, so I'll take one class, huh? Probably on Monday in the morning. Okay, this morning or evening. So which time will be better for you?
Sir, morning, sir.
So morning.
Morning, sir.
Morning.
Okay, so this Saturday I'll take from 10 to 11. Okay. Okay. Now
Yes,
I'm
sir.
just adding the PPT. So next class I will be discussing the estimation of unknown probability density functions.
So where do you share the PPT? Because I didn't get any link yet.
Okay, so because I already getting lot of message in WhatsApp also.